So a 0.08 kilogram hamster is on the outer edge of a 1.5 kilogram wheel, rotating at 2 revolutions per second. The hamster crawls to the center point of the wheel, and we want to find what the frequency of rotation is in revolutions per second when the hamster gets to the center point of the wheel. So this is my free body diagram, and this is our mouse or our hamster on the outer edge, and then this is going to be our center point here. So we're going to look at our initial conditions. First, we have the mass of the wheel plus the mass of the hamster because they're both on the outer edge. And then we have the radius of the wheel plus the radius of the hamster, or the distance of the hamster from this center point, because they're both on this outer edge here. And we also have the angular velocity of the wheel plus the hamster, because again they are both on this outer edge here, and the hamster is contributing to the wheel's rotational inertia. Our final conditions change because the hamster is moving from the outer edge to the center point, so it's no longer going to contribute to the rotational inertia of the wheel. So our final conditions are just the mass of the wheel, just the mass or the radius of the wheel, and then just the angular velocity of the wheel. But the angular velocity of just the wheel is what we want to find. So there are no external forces acting on this system. There's only gravity, because we're ignoring friction because it's so small. So in this case, our angular momentum is conserved. So we get to use this formula. L1 is equal to LF, or L final. And L is just the inertia times the angular velocity. We know that in this case, inertia is equal to the mass times the radius squared. And the angular velocity can be equal to a couple of things, 2 pi times the frequency, or the velocity over the radius. But this one is used for linear momentum, and that's not what we're looking for. So we're going to go with 2 pi times the frequency. So now we're just going to set our initial L equal to our final L, and then just plug in our formulas. Since L is equal to the inertia times the angular velocity, we have the inertia times the angular velocity initially is equal to the final angular velocity and final inertia. So then we're just going to plug in for I, and we have the mass times the radius of the wheel plus the hamster squared, times 2 pi times the initial frequency of the wheel plus the hamster. And it's all equal to the mass times the radius squared of just the wheel by itself, times the 2 pi final frequency of just the wheel by itself. So now we can cancel a few things, and we have the radius on both sides is going to be the same because the radius never changed. So we can cancel that out on both sides. 2 pi is going to cancel on both sides, but we can't cancel the frequency because the frequency is what is changing, so we have to keep both of our frequencies on each side. So we're left with the initial mass of the wheel plus the hamster, and the initial frequency of the wheel plus the hamster is equal to the final mass of just the wheel by itself times the final frequency, which is just the wheel by itself. So we want to find the final frequency here, so we're just going to solve for the final frequency by dividing by the final mass of just the wheel on both sides, and we're left with the initial mass of the wheel plus the hamster times the initial frequency of the wheel plus the hamster, all divided by the final mass of just the wheel by itself. So we plug in our numbers from the equation, and we get 1.5 kilograms plus 0.08 kilograms times the initial frequency of the wheel plus the hamster was 2.0 revolutions per second, all divided by the mass of just the wheel by itself is 1.5 kilograms, and we get 2.11 revolutions per second.